I am so glad to be here. This is my first visit to China. I arrived yesterday morning, and it's like I landed in a whirlwind of excitement and enthusiasm for robotics. I was over at the show this morning, and I just couldn't believe not only the number of robots, incredible, the number of enthusiastic people attending the show. It's really incredible what you've got going here. I love robotics and robots. And the initial inspiration for robotics for me actually came from animals. I was studying animals, their biomechanics, their neural control, and it's just really incredible what the physical systems that an animal can do. They can run fast, they balance, they use their perception, they have flexibility and compliance that contributes to their activity. You know, here these two animals are both running for their lives. One to stay alive and one to get a meal. And even human beings have great physical capabilities. This is my 2.5-year-old grandson demonstrating great coordination, hand-eye control, a little bit of knowledge about balance and mobility, and it's remarkable with almost no practice what a human being can do. I got started about 50 years ago, and I went to a conference when I was still a graduate student and saw this robot, and it's an inspiration. It was an inspiration not because its mobility was so good, it's because it was so terrible. And I looked at that robot and said, wow, they have it all wrong. Because animals fly through the air, they don't balance statically. Animals have kinetic energy when they move. They don't limit their speed so that that's not a factor. And I thought, well, maybe having 6 legs and 18 joints was too much of an impediment. So I decided, I'm a little bit of a contrarian. A contrarian, if a contrarian hears white, they think black. If a contrarian hears up, they think down. So I thought, okay, 6 legs, 30 million possible gaits. Maybe we should make machines that just have 1 leg. With a machine like this, you can't avoid balancing. There's only 1 gate, so you don't have to think about how to coordinate the behavior of all the legs in order to get those gaits. But you do have to think about balance and dynamics and control. And that's what we did here. And it turns out that if you can make a pogo stick balance, you can make a 2-legged pogo stick balance, do some tricks, and you can make a 4-legged robot that has dynamic behavior. And this was back in the mid-1980s, the early 1980s. Of course, there's hoses, there's an off-board computer in the next room because we didn't have the integration, the miniaturization that we have today. But we certainly were able to get at some of the fundamentals of what locomotion in a dynamic system could be. And I think those ideas have powered us ahead for the intervening years. Most of you are probably familiar with Big Dog. I'm not going to really talk about Big Dog today other than to show this one clip. But it's a robot that doesn't have pogo stick legs, but it uses many of the same principles and ideas. And even to this day, we're using some of the ideas that came out of thinking in a contrarian way. I think there's lots of opportunities for contrarian thinking in taking robots the next step. So up until recently, almost all the work I did focused on what I call the athletic intelligence of robots. That means controlling the physicality of the robot, keeping it balanced if it has to balance, controlling its energy, giving it mobility, having real-time interaction with the world and with obstacles or adversaries. But obviously for human beings and for animals, there's another aspect to our intelligence. And I think we could simply call that cognitive intelligence. You know, we think of cognitive intelligence as happening in our heads, doing things like making a plan. I had to go to the airport in order to take my flight to come to Beijing. I knew that the traffic was going to be busy, so I had to leave an hour for that, had to arrive at the airport 2 hours. Anyway, you can take a situation like that and use your head. You don't have to use your body to make a plan like that. Just you sitting here and listening to me talk, you're using your cognitive intelligence to understand the words I'm saying or the interpreter's words, and then relating them to things you know about in your lives. Well, about 2 years ago, I started a new organization called the AI Institute that's committed to combining athletic intelligence with cognitive intelligence. And I have to say that at the time I was proposing this was before the ChatGPT impact on all of our thinking in the world. So I don't know if we're catching the wave or being drowned in the wave of excitement about foundation models, LLMs. But it's certainly an extremely exciting time for cognitive intelligence. And just go look at the show floor here and you can see it's an exciting time for athletic intelligence as well. So our mission at this new AI Institute is to solve the most important and fundamental and difficult challenges in robotics and AI with a long time range view. We're not trying to make any products. We're not trying to make any money. We're trying to say, okay, there's a lot of problems that you can work on if you're working on products like reliability, cost reduction, and things like that. What are the things that are going to take us to the next generation? I don't know if in China, if Bell Labs is very popular, but in the United States, everybody thinks of Bell Labs as a place where you're doing free-ranging thinking about the future and how to develop technology that gets you to the future. And I would love for the AI Institute to become that for robotics and AI, purely focused on what it will take to get to the future generations of that. And we're focusing on 4 areas: athletic intelligence, like I've described and you've seen, cognitive intelligence, hardware. I think it's unfortunate that for many people, all the focus is on computing and algorithms and learning, and there's kind of ignoring of how important hardware is. I don't think that's so true here in Beijing in China, but I think it might be true across the board with current thinking. And so we have a strong focus on hardware as well as those other things. And in today's day and age, ethics in society, how robots are going to fit in, what people's fears are, trying to make those fears be reasonable, I think is an important thing. So we have a group at the AI Institute focusing on that as well. We have a lot of projects, and I don't have time to go through them all, but I'm going to give you a little sampling of the things we're working on. One thing that's mostly in the athletic intelligence category is building an ultra-mobile vehicle. And the inspiration for this, again, comes from human behavior. It's really remarkable what a human can do with a bicycle. I know you're supposed to just pedal them and ride, but you can jump them and bounce them and use your body weight and balance and use your perception to be able to plan the motions you're doing. So this is our aspiration, to be able to do this kind of maneuver. And we're just getting started. In fact, most of the stuff I'm going to describe at the Institute, because we're only 2 years old, is at the fledgling stage, not at the high-performance stage. We've designed some machines that let us explore this, and here's some early footage of these machines. Here's a little bicycle that can balance itself. We actually got a stock bicycle and added our own computers and actuators in order to develop behavior of this bicycle. So this is the balancing part of the bicycle, but we also want to make it possible for it to jump. So here we've been experimenting with the jumping part of the bicycle. So there's a mechanism attached to the body, which you can think of as the body weight of the person riding the bike. And we can throw that into the air or use it to absorb the energy of flight as the bicycle goes. And we're also working on a 3D version of jumping, and eventually we'll take all these pieces and pull them together in order to make an ultra-mobile vehicle. Obviously, there's a perception component and a planning intelligence component that have to be combined with those in order to make progress. We have another project called HALO, which stands for Human Athleticism, Learning, and Optimization. And this is being run by one of our people who comes from Marco Hutter's lab. Marco's sitting in the second row there, who is one of the pioneers in dynamic control and learning in robots. And I'm really excited about this project. I'm just going to buzz through the animation here. Basically, our goal is to be able to get to the high limits of environmental variability at the same time as the mobility of the system is at the extreme, and to do that through machine learning and intelligence. This is a clip from Marco's lab that was done separate from the AI Institute, where reinforcement learning is used to control the behavior of this robot. And what I find so exciting is that the whole body of the robot is available to use in getting mobility. It's not just the feet and the hands if it had hands. It's using perception. And this was all trained in simulation using reinforcement learning. And this robot can even go on rough terrain that's very irregular like this, using what it learned in a simulated world. And in a second, you'll see how you can use massive simulation in an environment that has various terrain features in order to build up the capability of the robot to embrace those features. We recently applied these techniques to the Spot robot. We got Boston Dynamics to open up a new API for us, which is a very low-level API where you can have direct control. And we used the same reinforcement learning techniques to get this robot to run about twice as fast as the release software that's in Spot. And I believe the software for this is all open source now, available, I think, through NVIDIA. If you want to know more about that, you can come ask me afterwards. Here's a different gate. We did a couple of experiments where the gate was fixed and we just optimized speed, but we also let the gate be flexible. And here's a case where we told the robot we wanted it to walk with 3 legs, not 4, so that it could use its free leg to do manipulation. We haven't done manipulation yet, but I think it's really exciting that a 4-legged robot could actually do manipulation if you freed up its legs, even if it didn't have an arm. I can remember a time at Boston Dynamics when we had a 4-legged robot and we could just barely get it to walk on 4 legs. So things have come a very long way since then. One of our cognitive intelligence projects that we're working on, we call Watch, Understand, Do. And the idea is not to have a room full of very sophisticated programmers work on programming the task of the robot, but to let the robot watch a human being do the task, watch it in detail, understand what they're seeing, figure out what skills are involved, and then do the task themselves. Here's the robot doing the task. Now, this is still science fiction, but I think with a combination of learning, foundation models, plus athletic skills, it's possible to make progress on a project like this. That previous slide showed an industrial application, but here's a domestic one, or at least a concept of a domestic one that could use the same kind of an approach. What's the next step after Watch, Understand, Do? That's Inspect, Diagnose, Fix. Imagine a robot in an environment that collects data, figures out whether a machine is working correctly, And if not, figures out what's wrong and then fixes it itself. This is further out, but I believe that someday we'll be doing that. And here's the domestic version of that too. We have an ethics and policy group that's, their mission is to collect real scientific data about some of the ethical issues. I think too much of the conversation about ethics and policy is driven by the media and by the fears, the Hollywood fears. I don't know, can I call it the Hollywood fears? The movie-making fears about what robots might be. And I think there's an opportunity to learn more about what that could be. I'm going to skip this because I'm low on time. And I want to give you a little update on Boston Dynamics. You know, at Boston Dynamics, they're working on 3 robots. The Spot robot, which is an ongoing product. The Stretch robot, which is in testing, but is going to be a product very soon. And then there's Atlas, which is the humanoid robot, the thing that's most tuned in, I think, to the audience in this conference. So I'm just going to say that there's about 2,000 Spots out there, you know, all around the northern hemisphere of the world. Not so many in the southern hemisphere, although there's some in Australia. And they're being used for a variety of inspection tasks, research and development tasks, digital twin creation, and things like that. And it's really remarkable the wide variety of things people have thought up to do with these robots. And of course, now there's other people developing the quadrupeds. I was just over at the Unitree booth. It's amazing what they're doing. You know, and there's Anybotics in, you know, a Marco spin-off company. And although you could look at these as competition, I feel like a market's being formed, and this is going to help all of us, and I'm excited by that. We've been working hard on Atlas. Atlas is a humanoid robot that's developed at Boston Dynamics. This is footage that you've probably seen before if you've followed us. It's a very athletic robot that has a lot of skills. This one is hydraulically powered. The company just showed a small clip of the next generation, which is an electrically powered one. And you know, I'm very excited about the level of dynamic controls that are used. This relies on model predictive control for much of its behavior, although they're starting to go beyond that. Very recently, they've developed the performance of the model predictive control to a very high level, and it's just amazing the level of stability that they've been able to achieve in this robot. I'm really impressed with how it can move and maintain its balance. But they've also been working on putting together a more complex sequence of tasks like the one shown here, where the robot's using not only its mobility, but its ability to use 2 hands to handle objects, some of them heavy objects like this wheel rim. It has a vision system that's used both to coordinate its interaction with the parts, but also for part of the navigation, so it can move through a space like this. Any of you who have worked on real robots moving in a space know that to keep the robot coordinated with an environment like this requires a lot of navigation and precision in the things the robot can do. So I'm really excited by this task and some of the others that the robot's been doing. In a second, you're going to see a task where the robot's manipulating those car parts, the struts, and putting them in a position so that they can be used in an assembly operation. Now this is the previous version of Atlas, which is currently retired. There's none of them working, so this work was done over the past year. And the company is in the process of switching over to the new electric Atlas. I'm almost out of time, so I'm going to skip ahead. As I said at the outset, it's an amazing time in humanoid robotics and robotics in general. Here's some of the companies in the United States making humanoids. These are from Europe. I put this slide together for China, but it just doesn't begin to capture the number of different people taking a stab at doing this. But it does raise a question, are humanoid robots a good idea? And I'm going to let that question hang because there's lots of different elements to the question, and I'm just about out of time. I'm going to show one more clip here. This is a time when we said, let's see if we could make the humanoid do some logistics task where it's handling boxes. And it's kind of fun. It can do this. It's using its vision, its thing, and you could have a couple of robots working together. But then we thought, well, if we wanted to make a machine that would be lower cost and have higher performance in a real application, you could simplify the machine. It still has some of the aspects of a humanoid, but it's a little bit simplified. And eventually that led us to this robot, a stretch robot, which is designed very specifically for unloading trucks. It has a vision system for doing that, and it has a manipulator and mobility for unloading trucks. And it can do pretty much the human rate at very extended times, pretty low failure rate. And we have this at testing in a couple of different companies. It's handled millions of boxes in warehouses, in real warehouses, doing real work. This just shows into the vision system. So I think the answer to that question of are humanoids a good idea depends on your goals. If your goal is to create the next generation of our dreams of what robots can be and to have them up to human capabilities, that's my dream, then I'd say go for it. Humanoids are a great idea. If you're trying to make money next year or the year after and you want to commercialize something at scale, I think that there's lots of ways at getting solutions. It might be humanoid, but I think that there's lots of other ways you could go at it. I know I'm over time, but I'm going to indulge myself in just showing one or two more videos, and that is about the culture of robotics. For me, there's a number of elements, and I don't have time to go into all of them, but one of them has to do with my love of robotics, and that's to have technical fun. And I think one way to do that is to make the robots express themselves, to perform in the world. I don't know why that stopped. Everybody here know who that is on the left? So thank you very much.